Good day, everyone. So today we'll finish up on naming our series. So we left off at aldehyde and ketone. So today we'll do carboxylic acid and esters. Let's start here. We have carboxylic acid. So here you also have to know the general formula, the functional group, the suffix, and how to identify one. So the general formula of carboxylic acid is CnH2n plus 1 COOH. Then the functional group is carboxyl group. The suffix, that's oic acid. To identify one, you have to have a structure like this one. So at the first or the last carbon, so at the first or the last carbon, you'll see a C atom bonded to O with a double bond and also bonded to OH. That's how you identify one. So let's do naming for carboxylic acid. I'll also do 2 examples for each. So A, here's our structure. So since now we have carboxylic acid and it's always at the first or the last carbon, the position of the longest chain is not important, right? So I'll rearrange my naming convention. So it's going to be position of the side chain, the prefix of the longest chain, and the suffix. So let's identify the longest chain favoring our homologous series. So the longest chain is going to be 1, 2, 3, 4, 5. Can circle that. Then choose a numbering from the carbon with a double bond of O and a bond of OH. It's 1, 2, 3, 4, 5. So I'm doing this in case you have a side chain so that you can know the position of one. So in our case, we don't have any chain outside of the longest chain. So we'll ignore that part for now. Then what's our prefix? We have 5 carbons. So 5 means pentan. Then I said we forget about the position. So what's our suffix? For carboxylic acid, it's oic acid. So join the oic acid. So the full name is pentanoic acid. Let's do one where we have a side chain. So we identify the longest chain favoring our homologous group or homologous series. So our numbering will start from that carbon. So it's always at the first or the last carbon, so you don't have to worry about that. So it's 1, 2, 3, 4, 5. Someone might say 1, 2, 3, 4, 5. So any order that you choose is fine. Then we circle our longest chain. Then use our naming convention. So it says position, side chain, prefix, and suffix. I'll repeat again. Here we don't have a position because the C atom bonded to O, double bond of O, and OH is always at the first or the last carbon. So let's name the position of our side chain. So we know it's in position 4 and it's 1 carbon. So it's methyl. Then the prefix, we have 5 carbons, and it's pentan. And the suffix, it's carboxylic acid. So the suffix is oic acid. So the name is going to be 4-methyl pentanoic acid. Then let's do the last one. I was supposed to do this when we do organic reactions, but for the sake of us understanding isomers and all that, I'll do it here. So we have what you call ester. So under ester, you have to know the general formula, the functional group, the suffix, and how to identify one. So the general formula here is CnH2nO2, if I'm not mistaken. Then the functional group, carboxyl group. Then the suffix is oid. To identify one, the C carbon bonded to a double bond of O, and O is in between 2 carbons. I hope it does make sense. So let me show you the process of how to find an ester, and we try and name one. So to form an ester, you need alcohol and carboxylic acid and a catalyst, which is H2SO4. So let's do our process. Alcohol plus carboxylic acid we use a catalyst, which is H2SO4, that's sulfuric acid, to form water and an ester. Let's see how does it work. I'll take any example. So under alcohol, I'll choose ethanol. Under carboxylic acid, I'll choose propanoic acid. So we know that we have to use a catalyst to form water plus ester. Let's see how does it work in terms of structures. For alcohol, we have ethanol, so it's 2 carbons and a bond of OH. Then for carboxylic acid, I said propanoic acid, so it's 3 carbons. For the sake of explanation, I'll write the C carbon bonded to O, double bond O and OH at the first carbon. So we need a catalyst, H2SO4, to form water and an ester. Let me write this in a way that you can understand. So what's going to happen here, the alcohol will donate OH, and the carboxylic acid will donate an H to form water. Then we join the 2 parts. It's going to be C. Let me use a different color for the other join. O, C, double bond O. So just for a reminder, a carbon can only be bonded to 4 atoms, right? So when naming an ester, I like to classify this part as our side chain. How would you identify that? So if you don't see any double bond of O on the C atom on its side, then you classify it as a side chain. Then the rest will be for your prefix and suffix. So here's our longest chain. And here is our homologous series. You can see it's an ester. So when naming one, you'd call it, what's the side chain? It's ethyl. The longest chain on the other side, it has 3 carbons. So it's propan. Then what's the suffix of an ester? It's oid. So we'd call this ethyl propanoid. For now, I'll do one example, and in the near future, I'll dive deep into this. So before we end our session, I'd like to add another part on isomers. So the first isomer that we are going to do is what we call a chain isomer. It's same molecular formula, but different structures. Let's look at one. So we look at butane or butane and 2-methyl propane. If we were to draw the structure of this, you'd see that it has a different structure compared to each other. Or if you were to draw structures of these two IUPAC names, you'd see that they both have a different structure, but the same number of carbons and the same number of hydrogens. So here you have but, it's 4 carbons. Then A, it means that we're dealing with a hydrocarbon which is saturated. Let's look at our second structure. The first thing when drawing a structure, we start at the name. So it's propan. So it's 3 carbons, 1, 2, 3. Then it's ane. You know that it's saturated, or there are no double bonds or triple bonds. Then our side chain is in position 2 and it's methyl. I'll do it then. So if you were to check the number of carbons and number of hydrogen in both structures, you'll see that they are the same. What's the general formula of alkane? You know, it's CnH2n plus 2. How many carbons do you have in the structure? So it's 4. H2 times 4 plus 2. It's C4H10. So you can see the molecular formula is C4H10. Let's check for the other one. It's an alkane, so the general formula is CnH2n plus 2. How many carbons do we have? 1, 2, 3, 4 times 4 plus 2. That's going to be C4H10. You have the same molecular formula, but different structures. That's what you call a chain isomer. Let's do a different isomer. Let's do positional isomer. I'll do 2. So how would you explain a positional isomer? A positional isomer is the same molecular formula, but different position of that functional group. Let's look at 2 haloalkanes. And let's look at 1 bromobutane. If you had to draw the structure of this one, we start with the name. So it's butane, it's butane. But means 4. Carbon, so it's 1, 2, 3, 4. Then the side chain is in position 2, and it's a bromo. For this structure, it's butane also. There's 4 carbons. Then it's in position 1. So if you were to count the number of carbons here, you'd see that we have 4 and 4 at the other side. The number of H atoms is 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Then we have a bromo in position 1. Here we have a bromo in position 2. So in simpler terms, you have a different structure, but the molecular formula is the same. Let's do a different one. You can also classify this one as a positional isomer or a functional isomer. But for the sake of you being able to differentiate, I'll do it as a functional isomer. So how would you define a functional isomer? A functional isomer is the same molecular formula, but different functional groups. Let me do 2 examples. I'll do one for ketone and one for aldehyde. Let's use butane 2,1 and butanol. So we'll use 2 groups, right? It's ketone and aldehyde. For our structure, for ketone, we use butane 2,1, and for aldehyde, we use butanol. Let's draw the structure. So it's 1, 2, 3, 4, and the double bond is in position 2. 1, 2, 3, 4. So that's position 2. Then you can fill the rest. Same thing here, we have butane or butanol. So but means 4. 1, 2, 3, 4. So for our cases, an aldehyde, we know its functional suffix is all, and it has a double bond at the first or the last carbon. So anyhow you choose, any process that you choose or any order that you choose will be correct. I made a mistake. I made a lot of bonds there, and the carbon can be only bonded to 4 atoms. Let's finish up the rest. So you can see that they have the same number of carbons, they have the same number of hydrogens, and the double bond of OH. The difference is that the double bond of OH on the C atom for ketone is in position 2, for aldehyde is in position 1. That's the functional isomer. So you can always assume that ketone is the isomer of aldehyde. You can use this one as a positional isomer and also as a functional isomer. Let's do the last functional isomer between an ester and a carboxylic acid. If you check the number of H atoms, we have 4, so it's 1, 2, 3, 4. Same applies this side, 1, 2, 3, 4. and the C atom bonded to double bond of O and a bond of O is similar. So these two are functional isomers. In summary, ketone and aldehyde are isomers. Ester and carboxylic acid are isomers. Then, in summary, ketone and aldehyde are isomers. Ester and carboxylic acid are isomers. Hopefully this was useful, and catch up next time.